Hello, hello. Okay, let's get started. So I wanted to take a couple of minutes to talk about debugging because this is going to be important. I mean, it was important even for the previous assignments, but I'm sure you probably all tried at some point. When you started with programming, you would typically use sprint-based debugging. So you'd print the variables, print their shapes, and obviously the read, evaluate, print loop, REPL, which is Collab or Jupyter, will kind of let you do that, right? So you can actually investigate what's the shape, what's the size, what is the type of the object, and all that. Okay. Obviously, you can print it if it's a Python program, but if it's part of Jupyter, then you can also do a lot of like repeat and copy the code and try something else. So you can many things you can do. But the next step, and maybe some of you have already used it, is to use the Python debugger. Obviously, if you're using a full-fledged IDE like PyCharm or like VS Code or something, then you can do a lot more than just this. But this would be the next step. Like if you're using Collab, one of the ways to debug is to use Python debugger, which is in the standard library. So you just have to import PDB and you can set basically what is called a breakpoint. So basically, you want to run the program up to that point, and then you want to get a sense of, okay, what's the shape of that variable? So let's say maybe there's some error happening, some expression. So right before that expression, you want to see, okay, what are the inputs that I'm giving to that function call, or what's the shape of my tensor, for example, right? So this is a handy utility you could have used actually for all the assignments, but also definitely will make sense when you work on your assignments, work on your project. So I just opened one of the examples that we briefly saw in our lecture. It's called LoRa, this low rank adaptation of, I think this is the MNIST code from some time ago. So I just imported PDB, that's it, that's one extra line. And other than that, I'm at some training loop, and what I did is add one line here called set trace. So, okay, so this is just, so the two lines essentially will get you some extra flexibility that you need. So I just said set trace there. Instead, I should have put somewhere else, but this is just some training code, okay? And don't worry about this exact structure. I mean, your code will be might have some slight variations. So here I've actually, you can see this green arrow here is actually showing where after setting the trace, which means that when I ran this training function, this function call is just called right below here in the last line. And when the function is called, each of these expressions gets evaluated, right? Instantiation of the cross entropy loss function, instantiation of the optimizer object, some variables are set to 0, and then you enter the trace. So when you enter the for loop, this is where what you'll get is actually not the best, but you'll get basically sorry, it's not scrolling down. You'll get basically a box like this. Okay, so I'm going to repeat this, but I just wanted to show you. You get a box like this, and then you can see some, shape of the variables, which is what I'm seeing here. Okay, so how did I? Okay, let me actually stop this. Actually, not stop, but I think I think it's running the full epoch. Okay, let's just stop this. Okay. Sorry. Let me clear all this. Yeah. So, as I said, just to recap, originally the code was something like this, and I wanted to get a sense of, okay, what's the data in the data iterator, okay, or whatever this data loader that we have, which is data iterator is just a kind of essentially the same as data loader, but an extra nicety, which is TQDM, is an extra package to kind of show the progress as you're iterating through your data loader. So let's say you set the trace here. Okay. So and then let's run this. So you can see that the function was called, the train function was called, and we went through some steps, some equations, some expressions, sorry, and then we stopped at where we did the set trace operation. Okay. So and here you can say, okay, what happened up to this point is we just iterated, we just sought, we got one data object from our data loader, right? So here you can check, okay, what is the type of the data object, right? So it says it's a list. Okay, so it's a list. So generally, if you're doing supervised learning, right, you have a label and a input feature. So it's a list. So we can obviously look at number of elements and all that. But so for example, I just did this right before the class. So it's a tensor. Each element in the list is a tensor. So you can see what is this, what is the size of this tensor. Okay, so this will give you a sense of, okay, what's the batch size, what's the what is the image here. It's an MNIST image based problem here. It's just some MNIST classification problem. So that's why you can see what the dimensions are. So you can see that, okay, 28 plus 28 is the image size for an MNIST image. And yeah, so let's see. So where is the train loader defined? Yeah, so here you can see that, I mean, in this script, train loader will define with a batch size of 10, and that's why the first coordinate is 10. Okay. So this is one way. I mean, it's not so much, I don't want you to focus on the exact script here. You can pick any script, any of your 3 assignments that you submitted, pick up a part which is actually computing something, and you can use this debugger to get a sense of dimensions and so on, which is where I think some of the challenges lie. Okay, you can also obviously add a debugger anywhere else. So in the definition of your model, I don't know where the model definition is. Yeah, like for example, you can say inside the forward pass, you can put a debugger just so that anytime the function is called, you can stop and see, okay, what is the input? You don't have to do it all the time. You just check once that the dimensions are correct and it's going to the right set of transformations, linear layers, and so on, right? Yeah, so very useful beyond print debugging. You can also do print debugging, but this will give you a flexibility to step, some extra things. So print debugging, you print, but the program continues to run, which could be an expensive operation perhaps. And so here you can stop and you can step through one expression at a time, or you can say, okay, continue throughout the program. So there are many choices, and you can look at the I mean, this is from the Python standard library, so you can look at, okay, so you can do this, or you can actually also apparently call breakpoint. And you can, there's a bunch of functions, not functions, but the commands that you can give once you enter that small box that you saw. So you can type h to see what are the options available, right? I think here, we are still in here, so we can just type h to say, okay, these are all the commands available. So basically you can go next, you can quit, and you can do many things. So if I quit, obviously the debugger will stop. So then it will just do the epoch specific, all the training that you want to do. So once you exit the debugger, then the breakpoint is kind of invalid. Now, if you use VS Code or PyCharm, you can actually use UI to kind of denote a breakpoint directly. You don't have to explicitly add you need to be in the debug mode, which is some choice at the top bar. But once you're in that mode, you can enable and disable some breakpoints by just using your cursor, and just tapping at one of the expression line number, and just you'll see indicators, okay, visual indicators. So here we are not doing it because I just wanted to show you the minimal functionality. Any questions about this? It seems kind of trivial, but it's going to be very useful if you are looking at errors, especially, right? So you can email people, you can search on, okay, copy the error command and copy it onto, search on internet, whatever, web search engines. That's also fine. I mean, other people would have hit the same error, but it's also good to, use a debugger also. So it's it actually boosts your performance. In addition to, of course, if you have the opportunity, also use an IDE, because it has IntelliSense, so you can actually get the function signatures, all the potential functions that are possible, let's say in an object. You can get all those completions depending on how you configured your IDE, but by default also you'll have a lot of these options. Okay, it's called IntelliSense in I guess VS Code, but there are other, I guess, different names for this. Of course, the next step is then to also use Copilot and variations like that, which are I would say like the next step to IntelliSense. So they'll actually fill up at least simpler functions and simple functionalities. You can actually just ask a AI model to generate for you, and these are just language models, okay, trained on code data. Okay, then let's actually get back to our objective, which is this, not this. Okay, I left it as is, that script, but it's okay. It's gonna leave the resources in a second. So we are here. So in the next week, we'll have a individual meeting with each team, and that's an important milestone because it also has some grade weight associated with it. I think it's 10% of the 60% weight for the project. 10% is for the intermediate submission, which is actually really a checkpoint of, you don't have to do, you're not completing a project, but you need to have a full plan of what you would like to do or what you would be doing. And then the plans get revised all the time. And one of the checkpoints is we'll have meetings with me. So I might update this Zoom link that's there on the Excel sheet. So on the Excel sheet, I think 3 groups, at least half an hour ago, 3 groups had signed up for slots. But the remaining 4 groups should sign up as well. It's a 15-minute slot, and basically in that slot, you should just join the Zoom link that's there on that page. Okay, I'll update the link. I guess I'll just double check that the link works, basically. But so that's what you're doing by next week. So don't think of it as it's the same percentage as your assignment. So it is important to be on at least in the right starting trajectory so that you can actually accomplish something interesting by the end of the session. Okay, and yeah, so this part next week will be online, so you don't have to come here for just 15 minutes. So that's important. Okay, no other students who are not in that. If you're not meeting in that period, you're fine, you're free, but then hopefully you front load the work so that when you come to that meeting, you need to have something concrete. Okay. Okay, so today what we'll do is continue where we left off. So let me come back to this lecture goal slide. Last time we just started, just meaning of, I guess, unsupervised learning mostly, not so much generative modeling, but generative modeling just means you're modeling everything about your data, not just conditional probability of some label given input. And so the word generative just means you could, because of the model, you could actually generate new data points. Okay. So which doesn't make sense for any supervised learning problem, because they are all about assigning a label or a point estimate given some input, but they're not modeling the input itself. Okay, modeling as in there should be some distribution or something like that, that from which you can get a new input if needed. Okay. So last time we stopped where we were discussing about autoencoders, and we'll continue that discussion and talk about variation autoencoders today. There is actually a code base that we'll look at right after the discussion. It's in the PyTorch examples. PyTorch repository has an examples folder, and within which there are lots of implementations. One of them is VAE, so we'll look at it. And then the second part of the lecture, we'll look at what are called GANs, generative adversarial networks, which, as I said, all these are just gadgets from which we can sample a new object. Okay, it could be an image, it could be a vector, it could be whatever. So so we look at a different model. One of them is an explicit model, where there is an explicit joint distribution between some hidden variables and some observations. Observations being images. We're mostly talking about images here. and the second one, which is GAN, is basically an implicit modeling approach where we're not talking about distributions anymore. At least the gadget that we build, there is no direct interpretation of it as like a conditional probability or something. And yeah, so the goal is just to intuition behind GANs and and some differences and similarities between GANs and VAEs. Okay. Note that although we're talking about images in mostly towards the end of last lecture and today's lecture, they're not specific to images only. So you can work on any type of inputs, outputs here with unsupervised learning, right? Typical inputs, vectors, images are just matrices, but you can also work with other structured objects, mostly graphs. Graphs are also actually represented using matrices, so it's not really that big of a difference from a graph to a image. So you can actually process graphs. You can project graphs into lower dimensional space and do some unsupervised learning or unsupervised exploration there. Okay. Okay, so that's the goals. Any questions about today's session? Today's session is just about understanding VAEs and understanding GANs, at least at least one pass on them. I mean, obviously there are a lot of variations in the literature if you actually search for them on Google Scholar or something, but we look at the canonical versions. So VAEs were proposed first in a paper from 2013, so I guess 2014. This is a paper which appeared, no idea, which appeared in 2014, I guess, some conference in 2014, I think ICML or NeurIPS, one of these top machine learning conferences. And the GAN idea, so actually both these models, it's not like they're completely new. I mean, there was already pre-existing some prior work, but the name, the key turning point from which they became their own, I guess, subfields is from this 2013-2014 paper, and also GANs came about in 2016. Okay, so these are not that old models. Okay. Yeah, actually, before I jump into the actual slides, I wanted to open this. Actually, this is a paper from this year, just to give you a sense of what's possible today. Okay, so this is I'm talking. What we're going to look at in the lecture is going to be from 2016 era, but 2023. This is a paper published in. Let me just see what the name of the paper title. It's called SIGGRAPH. And the underlying technology is actually GANs, okay, that which we'll see in the second half of this lecture. What they're trying to show is how to manipulate images. Okay, so and actually they're generated images. It's not actually from some database that you're just editing. Okay, this is what is possible, and I guess that's what I guess call it drag your GAN. But obviously it's not base GAN. There's actually extra tricks and ideas to kind of get to that point. And the second paper I just want to mention is called I guess GigaGAN. But basically these folks from Adobe Research and some other places, POSTECH and CMU, this also came in a top conference. I think we've discussed CVPR a couple of times before, but top conference this year. Where what they're trying to show is to compete with something called stable diffusion. I don't know if any of you have played around with DALI 2 or stable diffusion. So they're all some machine learning models where your input is a variable length input, which is a text sequence, and output is an image of a fixed size. Okay, so it's a variable length input and a fixed size output, but then the model definition is, we've not seen the model definition in this course yet. So that's, I guess, more popular way of generating images given a text description. So you just write a prompt and you get an image back. So this paper is showing how to do the same with GANs. Okay, so even GANs have an advantage because they are a little bit faster than, I guess, as they say here, orders of magnitudes faster than those other models. Okay, diffusion models we haven't seen in the course yet, but those stable diffusion, the word diffusion comes from a certain type of model family. Okay, so here you can see, for example, the input is going to be, this string here, portrait of a human, you know, hyper-realistic oil painting and so on, and this is the output. But anyway, I mean, today's state-of-the-art models are very good like this anyway. But this is the second example of what's happening today in 2023. Although the material we're looking at is from, let's say, 2013 to 2017. Okay, it's more basic. Okay, so with that, let me go back to our slides. Any questions here? Yeah. Augmented reality is not a specific technique, right? So here it's even both. You're talking about the second application or the first one? The second one is just going from an image, sorry, from a text to an image. That's just prediction again. So it's just generating it's sampling a new image given a context, okay, context information, which is a text variable length input. So it's just the opposite of image captioning. Remember, we saw image captioning where a fixed size input and then there's a text output, and you had to, your training data would have the image along with some strings of descriptions, and then given that input output pair, you just build a supervised learning model. Okay, that's a specific technique. Image captioning is a problem, and then there's specific techniques to do that using RNNs and stuff. The example that you saw is just the opposite, and I think that has a gap from augmented reality, which is I guess the umbrella term for many different types of technologies. Which, as I guess the phrase suggests, it's augmenting reality. So overlap, I guess I don't want to define it here, but you know what AR is, or AR and virtual reality. Virtual reality is completely, it's not augmented with the real physical world, but augmented reality you can overlap projections and different things on real world with which a user or a human can interact with, right? So AR is, I guess, a broader technological term, a broader term, whereas here we're talking about specific techniques, specific problems, and specific models that solve that. So the GAN is, you wouldn't think GAN can be used for that, but some researchers have shown that you can use GANs for that. Okay, that's what we'll cover today. What is the basics of a GAN? Okay, so what I'll do is, last time we briefly covered autoencoders. We just will recap that and then really get into VAEs. So actually the material is somewhat light today, and so one of the objectives is also to look at the code for VAEs. So maybe that's going to take some time, but let's see.
I have a quick question.
Yeah.
You have an opinion on the ethical implications of generative models, either for, like, say, the art industry, or how the data is sourced?
Yeah, so there is a lot of challenges there. Here we are not going to talk about that, but that's a very important aspect of generative models in general. There are multiple aspects actually, but the question you asked has intersections with things beyond like what this course was focusing on. But that is actually a very big component. In fact, maybe we should spend some time on ethics in general. Not just on the generative AI side, but also as increasingly many AI models are being used to make automatic decisions in not just private sector, where, for example, you get a recommendation from Netflix. That's okay. It's a private company building some recommendation models, and a deep learning model potentially, and showing you recommendations. But also in the public sector with applications for subsidies, or housing assignments, or school choice. Many of these things are getting influenced by some black box somewhere in that pipeline, and so there is downstream. There's multiple societal effects of those things, right? So that's so there was some. So I haven't created that material, but that's actually a full-fledged courses for that. I'm not sure, maybe the CS department, but also other universities. But we're not touching that, just to not complicate and add too many topics. But it's a good point that you added. I would have said that as a disclaimer, but it is a very important aspect here. For example, this text to image problem. I think Adobe, for example, has a product. I don't remember the name, Firefly or something. But they have created this model, but they claim that they have only used their license. They have a huge inventory of images on which they have trained this AI model, and so they're differentiating themselves compared to somebody else who just scrapes images or does not credit the artists who actually had the original works and built the generative model, right? So, but there is a very important consideration. That's all I will say. Yeah. So there is actually interesting ML problems, technical problems that come from that. For example, let's say you train a model and post hoc, let's say an artist says, I want to remove all my data from your model. So what do? Do you delete the data from the input and then retrain the whole thing, or is there a way to change the weights? It's actually one of the questions. I think Google is running a competition right now, which they're just sourcing, I guess, asking researchers and students how to do this right now. But the larger problem remains, and so there has to be inputs from law and other disciplines to kind of figure out something that works. Yeah, so let me come back to this. So as I said last time, we look at basically two approaches. Under each approach here just means there's an explicit approach and an implicit approach. And it's just broadly and very informally just saying that explicit approach just means we're going to explicitly talk about a joint distribution. It's a generative model, so there has to be some joint distribution, some distribution over data, like which completely models the data. Okay, so there's not going to be some conditional probability. The starting point is going to be some full distribution over your data. In this case, the data for our lecture purposes is going to be images, but as I said, the models you can apply it to other things. So we look at VAEs as one type of a gadget to get these new data points or get sample new data points, and generative adversarial networks is another way to also sample new data points. Okay. So what I mean by that, basically the generative process, once you have trained these AI models, the process is just that what you get once you train is some sort of neural network, okay, and that's in yellow. And you need to start with some source of randomness, because if you want to have a distribution from which you want to sample, there has to be some source of randomness defined. So the source of randomness generally is going to be some distribution, like a Gaussian distribution, and from which you first sample a vector, and then you pass it through this neural network, and then you get an image. Okay? And the hope is that the distribution that this is representing kind of corresponds to the distribution of images, for example. Okay, which is kind of hard to imagine, like what does the space of 1 megapixel size images look like, natural images look like. It's a I don't think you can really quantify how it looks like. So with that, that was the overarching goal. Okay, today we just want to create that yellow object from which we can sample new images. But to do that, we are going to talk about the two modeling approaches. The first one is variational autoencoder, and it's basically an idea which improves on autoencoders. And autoencoders by themselves are, have their own pros and cons. But last time when I discussed them, I was talking in terms of, okay, you want to project data in lower dimensions. If you want to achieve some compression, then that's one way to do it. In addition to, like if you already know PCA, you're using PCA somewhere, you can switch over to autoencoders. There's going to be some pros and cons. Unlike PCA, there is no orthogonality constraint on the new space that you're getting into. But because there's no such constraint, you may be able to compress the data better. Okay. To discuss autoencoder, and also not just autoencoder, but variational autoencoder and GANs, there is this object which just is the opposite of what we have been seeing in the lecture 2 and lecture 3, which is instead of going from an image to some embedding, some activation vector or something. Here we're going from a vector to an actual image. Okay? And how do you do that is, you have to go from tensor to tensors. It's just that the final tensor happens to be like, doesn't have too much depth. So it looks like an image if it has 3 layers, right? But how do you go from a smaller set of numbers to a larger set of numbers? It's not, from the picture, it seems like, okay, we are just creating some extra numbers out of thin air, but it's not, right? So there's going to be some layer, and the layer will have parameters, and those parameters will be reused again and again to get these numbers. So it's not too far-fetched to create a bigger tensor from a smaller tensor. Okay, and if you really want to look at it, I think last time we just saw this slide where you can go from a 4-dimensional vector to a 6-dimensional vector, except that each element in this 4-dimensional vector will be reused many times. For example, here it's being, so the first coordinate of this 4-dimensional vector is going to be pretty much interacting with the first column here. And so you can see that the first number has been used 9 times. Similarly, the second number has been used 9 times, and so on. Okay. So basically, like this number is influencing 9 numbers in the output. One input number is influencing 9 numbers in the output, so you can go from a 2x2 matrix to a 4x4 matrix. So you can imagine, like, it's the same thing happening at a bigger scale. Okay. Any questions about this? This is from just last time. Okay, so once you agree that okay, there is an object, there is a way to kind of connect these layers, transpose convolution, or informally called decon layers also. You can go from a vector to a image, and obviously you have to train those layer parameters. Okay, and the operations are actually very similar to column operations. That's why it's just that's why it's called transpose convolution. It's just transpose is literally the matrix transpose type of operation. So last time, okay, so given that gadget, now we can talk about auto encoding. Okay, so the word auto and encoding. So let's talk about encoding. Encoding is just going from one representation to another representation. Here, let's say we want to start with, we want to think of, okay, for every image, let's say that there is a kind of some input code or some vector that kind of can represent that image. It's like a key value, right? So if I give this key and I have a box that produces a value, and the value happens to be the image. Okay, so that box here is a bunch of decon layers or transpose convolution layers. And you can imagine, at least if you have a single core and I want to generate an image, I can always train my network such that the weight such that when I give this as an input, I get that as an output. It's just an optimization problem, right? So it's just saying find the parameter such that if I give a specific input, I get a specific output. Okay, so this is very elementary. All I'm trying to say is that there's a way to go from a specific vector to a target, and so this is just the process of encoding. And obviously, where is the information captured? It's probably not in the vector once. There has to be some information captured in the these parameters of these layers, okay, decon layers, right? So information about this cat, like for example, literally just remembering the pixels of the cat if you want. Okay. And autoencoding is basically kind of expanding that idea from a single vector of ones to a image to a collection of vectors producing a collection of such images, and we don't even have to specify those vectors beforehand. We're going to learn those vectors by attaching the opposite operation, where we go from image to a vector, which we know how to do using, for example, the regular CNN. Just drop the last layer. So we know how to get to a collection of vectors. We don't have to pre-specify the vectors, unlike the previous illustration, and then those vectors can generate your images, and you can try to train these both encoder parameters and the decoder parameters to ensure that you are able to generate the image that was input. Okay, so this way you don't even have to specify the vectors in between. Okay, if you had to specify the vectors in between, that would be like some sort of supervised learning problem. For every vector, you could say a certain image. That's just a fixed input, fixed output problem. So we are kind of getting rid of that. Okay, so that's literally auto-encoding. Auto part just means that you're encoding yourself or encoding the input and comparing it, reconstructing itself. Okay. Okay. So what is the objective of this whole autoencoder setup? Is to do basically dimensional reduction. Okay. So basically, we want to capture some common information in a collection of data. Let's say there's a bunch of images of animals, then we want to kind of somehow go from those figures or images of animals to some lower dimensional vector space, so that some common patterns of, okay, maybe these are all mammals, and so 4 legs and so on, like that's captured in the weights of these encoders and decoders, so that the The vectors can differentiate between animal 1 and animal 2 and whatnot, but all the information is compressed into some lower dimensional space. Okay. Generally, your Z is going to be Z, which is the encoded space. I guess here it's being referred to as features, is generally lower dimensional and generally a vector, even if your X is an image, for example. Okay, so you start with an X, go to lower dimensional space, and reconstruct your input X. That's what you would do if you knew the parameters. If you don't know the parameters, you would just have images. You just want to compare the reconstructed image with this image, and if it's too bad, then you kind of adjust the parameters of the decoder and encoder to improve it. Okay, so your input is just X, which is just getting computed on, and then you're still regenerating X, but there is this bottleneck operation. Okay, there is this lower dimensional Z from which you have to reconstruct the full image. So there has to be some, basically you're learning some common patterns in a collection of data. Okay, that's the whole point. But if you choose Z to be the same dimension of X, I think we discussed this last time, then there is no need to, I mean, a trivial solution is to just have encoder being identity function and decoder being an identity function, right? Obviously, there are some applications where it makes sense to have Z the same size or a little bit bigger. Those are called denoising autoencoders. So it's something to do with noise. But we'll not worry about that. So canonical application is just getting down to lower dimensions. It's just compression basically, and turns out if you really want to compress data, this probably is not the optimal way. There are many ways to compress data, but this is one way to do it. Okay. So in this figure, it's just a thing, it's just expanding on the architecture from the previous diagram. So you are basically minimizing, you pass X, get some X hat, that's the forward pass, and then you're just comparing X hat to X using some squared laws. Okay, element-wise, if X and X hat are like vectors, then element-wise comparison, 2-norm difference in square of that. But you can choose any other way to compare these objects. Okay. And as I mentioned, the connection to PCA is that just like PCA, basically, if you learn the encoder, then any given new data point, you can potentially compress that into some feature space and hope that you'll be able to reconstruct the point, with high quality. So that could be like a compression, operation. But also the hope is that, by doing this, you're kind of removing kind of irrelevant idiosyncratic parts of these input images, and some common related aspects are captured in the vector Z, in the vectors Z. Okay. Yeah, so autoencoders can be used, autoencoders as well as VAEs can be used to kind of model these low dimensional representations of these high dimensional objects. Okay. And there is still a kind of a issue with the autoencoder technology, is that it's not really made for generating new data points. Okay? And also this encoding, your focus is just the reconstruction error. So it could be that, let's say, for example, the two very similar images of like cats, both images, they could be encoded to very different vectors just because the reconstruction error is low, and you could still be able to reconstruct them. But that's not something, that's not very desirable. Ideally, you want similar images, or images of similar objects, for example, to encode into the similar location. Okay. PCA does that just because it's a linear transformation. So if two things are similar in the input space, then they will be similar in the lower dimensional space, just because it's a linear transformation. But with autoencoders, the encoder and the decoder, they generally are neural networks, and so it's not, there's no way to kind of ensure that you're actually projecting now into the same region for similar objects. Okay, so that's one thing. And in general, as I said, you can't really sample objects from this from once you learn the encoder and decoder. Okay, it's not like, oh, if you already encoded and you learned the encoder and decoder, it's not like you can now specify a Z and then generate an image, and as you kind of perturb in the Z space, as in like you slightly vary Z, it's not like, let's say if it's a cat, if you slightly vary Z, it doesn't mean that you get some other like cat-like image. could be completely different. It's just that there is no. It's just because we're only focusing on reconstruction error. Okay, and these constraints. So it's not as constrained as you would want to kind of be able to represent similar data in similar spaces and so on. Okay, so this is one issue. Otherwise, if this issue was not there, you could still make some, you can add some bells and whistles and still make you can still sample from this object. Okay? And that's exactly what we'll do next, which is to add some extra capability or some changes in the loss function and so on, so that we can sample things. And if you're in a similar region in the Z space, if you're slightly perturbed in the Z space, you will actually get similar objects sampled. Okay. So that leads us to variational autoencoder. The word variational, as I said last time, is just something to do with approximation. Okay, but there are two steps here. First, we wanna endo this original autoencoder with some probabilistic model definition. Okay, which means basically we're gonna endo it with some probabilistic graphical model. Okay? It's going to be a very simple model with just two random variables and one edge between them. But that will be the model definition. And then if there are two random variables involved, then there's going to be joint distribution between them. And what we'll see is the second step is going to be some approximation of the joint distribution, and that's the variational part. Okay, so there basically the original autoencoder architecture that you saw is that's the starting point. We'll now endo a joint distribution on it, and then approximate some part of the joint distribution, and that's what's going to lead to the variational autoencoder fully. Okay, so basically what we want to do is now start talking about random variables. In the previous picture in the autoencoder, you already saw that there's a x and there is a z and there's an x hat. So you can imagine, okay, there's an x and a z. Let's not worry about x hat for a second. We can just call them random variables. Okay, and obviously on the x side, if there's a bunch of images, you're thinking of a distribution of images. That's, as we already discussed, it's a complex object. But the z space, if you think of z as a random variable, we can choose choose some distribution on it, and in this particular architecture, they specify a specific distribution on z. Okay, you can say, oh, why do you have to choose a distribution on z? Let that also be a unknown thing, just like the input distribution or images is an unknown thing, we don't know. But in this model definition, we have to there are two variables, x and z. Our data is only of x, that's why z is a random variable, z is a latent random variable. And to define the model, we have to kind of at least in this architecture or in this model definition, you have to at least ground what the distribution of z is. Okay, because first of all, we don't know what the distribution of x is. P of x is not known. So, and if you don't even know P of z also, then what is that joint distribution? Okay, so we have to, so the starting point is we assume that P of z is a Gaussian distribution. Yeah, and this is actually ties back to that previous point I was talking about, that if we restrict z's to be Gaussian distributed, then you can talk about, okay, slight perturbation probably should retain, let's say a z corresponds to a cat image, then some area around z should also probably capture the same kind of cat-like images. Okay, so that's some restriction, that extra restriction that this allows. Okay, so we made z a random variable, we made x a random variable. So that's good. And one of there are a couple of ways to discuss this VAE, by the way. So one of them is just talking about changes in the architecture and changing the loss function and done. So you don't even have to talk about anything to do with variational approximation of a joint distribution. Okay, you can do that, and we'll do that actually first, and then we'll talk about the let's actually talk about the joint distribution. So the first cut will be just change in the architecture, change in the loss function. So by which I mean, we're first gonna just see what the changes are. Okay, so first the change in the loss. Remember previously in the autoencoder there was a reconstruction loss. Okay, x hat minus x, 2 norm square. So we're gonna call them reconstruction loss because we're reconstructing the input and then seeing how bad the reconstructed x hat is. There's going to be one more loss now, and when we're trying to do optimization, right? Remember, we have to train the parameters of the encoder, train the parameters of the decoder together. And so our objective function now is not just a square loss, reconstruction loss, whatever. But it's going to be there's going to be one more term which is called the latent loss. Some loss corresponding to what z values we decide and what z values the current parameters are generating. Okay, so that's the loss that we're gonna extra term that we're gonna have. Remember, in the model definition, we said, okay, we're going to make p of z to be a Gaussian random variable. Given the current encoder parameters, as you pass input training images, basically, then there will be some distribution of distribution over z space that you would get of the z random variable, and maybe they're not similar to each other because we want Gaussian. It will be some crazy distribution over z, and if the distribution is too different from Gaussian, then it's probably not a good parameter choice for the encoder and the decoder. Okay, so that's measured using a term or a function called KL divergence. We'll look at it in a second, but it's basically just trying to figure out what's the gap in the z space. Just like in the x space, we know what the gap is: x hat and minus x. That's the gap in the x space, and similarly, there's going to be a term for z space. Okay. We look at the why does this extra random thing pop out. There's a specific reason why that pops out, and that relates to the variational approximation that I was talking about. But for now, since we didn't discuss it, let's not look at it yet. Second is the change in the architecture. The architecture, what should be changed in the architecture? First of all, the architecture is going to be, we know how to send an input image, go to the z space, and produce back an output image, hopefully that's similar to the input image, while training at least, right? But now we want to have random variables, some randomness, basically, right? X is a random, we just said x is a random variable and z is a random variable. So how do we introduce randomness? Instead of going from an input image to a fixed z vector, we're gonna say, okay, instead of going to a fixed z vector, we're gonna go to a mean vector for the z random variable and a covariance, let's say, covariance vector for the z random variable. Okay, so those are random variable will have a distribution. A distribution will have parameters. At least those parameters are not going to be random. I mean, they can be random potentially in a more complex model, but we'll say, okay, the parameters are not random, so let me predict that. Let me encode them. Okay, which means that going from an input image, I'm going to first generate a mean vector and a covariance or a standard deviation vector. Okay, here in fact we're going to get a standard deviation vector. What are these vectors? So remember, we want to make the z space, the distribution on z, to be Gaussians. Okay, that's why we are focusing on Gaussian distributions. Parameters are literally two things, especially in higher dimensions. It's just the mean vector and the covariance matrix. Okay, in fact, let's simplify and say instead of covariance matrix, we have a diagonal covariance matrix only. So it's basically this kind of independent across coordinates, which means that your covariance matrix, instead of representing a matrix, you can just look at the diagonal vector. So diagonal vector, which will just be the variances of each coordinate, or the standard deviation of each coordinate, and then you have the mean of each coordinate. Okay, so there's two vectors you're producing. Once you produce those two vectors, then you can sample a z given the mean and the covariance, right? You have a normal distribution from which you can sample, and then that z, that sample z, you can pass it to the decoder. And again, here actually I'm not. I'll show it maybe in a couple of slides. But once you pass the sample z through the decoder, you can again get a mean and a standard deviation vector on the x space also, from which you can sample, and that's your image. Okay. Remember, our x and z's are supposed to be random variables, so we just enabling it by saying, okay, these encoders and decoders are not generating x's and z's themselves, but actually generating the means and covariances of the distributions on x and z, distributions related to x and z. Okay. So that's the change in the architecture. It's just you want randomness. So how do you incorporate randomness? This is one way to do it. You can choose. It's a choice. I mean, in the variational encoder that was introduced in that paper that I showed you, they chose Gaussian distribution. But there's some reasons. There are some reasons, qualitative reasons. But in terms of the definition of this model, you can change a lot of things. Yeah.
And the mean vector and standard deviation vector, are we defining that?
No, these are the so previously in the autoencoder, in the regular autoencoder, remember we're going from an input image, let's say 28 cross 28, that mness size, to let's say a 10-dimensional vector, right? So that was z. There was no randomness and stuff. instead of doing that, we're going to go from 28 cross 28 MNIST image to a 10-dimensional mean vector and a 10-dimensional standard deviation vector. So it's not predefined. These are just the outputs of the encoding process. Okay, so every image will have its own mean vector and a standard deviation vector. So yeah, but the assumption about the VAE is that the marginal distribution of Z. So marginal means so first of all, the moment you have two random variables X and Z, you have a joint distribution between them, P of X comma Z, right? Typically, right? You start with that. The marginal distribution is just average out all the X's that are possible. So if you average that out, then we are assuming that that averaged distribution on Z should be Gaussian. Okay, here we are saying that that was the assumption in the previous slide. Here we are saying, okay, that's the assumption. We can also per input image also we can make it assume that the encoder spits out a mean vector and a conditional, mean vector and a standard deviation vector, conditionally Gaussian also. Yeah, but you have a question?
No.
Any questions? So actually, architecture involves one sampling here and also another sampling there. I think there's a picture in the next couple of slides about that. So this sampling happens during training. Okay, so this is the just like in autoencoder, you have to do some grain, pass the do a forward pass and then look at the errors and then propagate it back to okay, how much should the parameters of which is literally the weights of this CNN essentially on this side and the decon network on this side, how much the weight should be changed, right? But here the thing is, if you naively look at it, or at least look at it first glance, you think, okay, there's some discontinuity here because I only produce the mean and the covariance parameters from which I sample something. And so how do I backdrop? I mean, what is the connection? What is the connection here? But it turns out it's although there seems like some discontinuity here, like a sampling step, you can still backdrop through this computation part, the computation part here. Okay. One of the, I guess, phrases here, it's called reparameterization trick. If you have come across or if you want to search more about it, it's nothing complicated, but I don't want to get into it. But it's just even if you sample something, you can still backdrop it. Yeah.
So you said the mean and standard deviation were of the coordinates. So for example, if you have a 28 by 28 and it's like,
let's say this is 28 by 28.
like 3 channels, and then
yeah, there could be 3 channels.
The dimension of the mean and standard deviation.
Yeah, this is you choose the dimensions here. So let's say you get this. Okay, I want my latent space to be only 10-dimensional vectors, 10-dimensional vector space. The mean is going to be 10-dimensional vector, and the standard deviation vector is going to be 10-dimensional vector. This vector is going to be facing the diagonal of a covariance matrix.
For all 3 channels, or
no? It's so the number of channels here has nothing to do with the vector space here. So you could have black and white images, you could have color images, but you want to go to a low dimensional space where it is some vectors, basically. So actually, the whole thing, what we're discussing, as I said, is not specific images. You could have vectors here, higher dimensional vectors. You could go down this low dimensional vectors also. Any other question? Okay, so the sampling is, as I was talking about earlier, this whole constraining Z to have some distribution is actually kind of letting us generalize. Actually, not just doing compression like zip, if you use zip, unzip, a zip operation, WinZip or something like that, you're just compressing data, right? So that's what essentially what autoencoder was getting us. Obviously, some compression with some reasonable projection down into lower dimension space, so you could do clustering and stuff like that. But what this extra, like endoing this extra loss term, the KL loss term or latent loss term, or just thinking in terms of X and Z to be random variables, is letting us basically do generalization, which is what we want. We want to sample, we want to train on some training data set, some 1,000 images or 10,000 images. But once we learn the encoder and decoder, we want to use the decoder, for example, to kind of generate new images. Okay. So obviously Gaussian, like the sampling step, for example, ensures that you're not just remembering only the training data. Okay. Because if you remember only the training data, obviously your reconstruction error will be good, but then there is your latent loss will typically not be good. Okay, it will be high. Okay. So this is from some reference here, but basically they're showing this is the training part. This is actually the original images, and as you train, you're getting better and better generated images. Now you can say, okay, how do I know that the generated images are not exactly just remembering some input images? There are ways to do that. It's just to debug, like you're not just remembering just training data only. There are ways to do that, but MNIST is such a small data set that it's kind of hard to see, but this is what you would get. Okay, it's just showing a sample of a bunch of images during training. So if this is the input, you should get all of the same type of output. Okay, while you are ensuring that the distribution on Z space is Gaussian. Okay, so now we'll switch to the actually interesting stuff, which is to kind of reason a little bit more clearly why there is a different loss function here. Okay, the different loss function just comes from us trying to maximize likelihood, and so when you try to maximize likelihood, you have some challenges, and so you need to make a variational approximation or basically some approximation of this joint distribution, some aspects of this joint distribution, and that's what leads to a nice reconstruction term and a latent loss. So there is a very principled way, because you had random variables and you had joint distribution, you made some assumptions, and that led to this loss function. That was missing in my previous narrative. Previous narrative was just, okay, we're going to just change some architecture, and we're going to tack on an extra loss function. That's not very clear. Okay? That's clear from just operation point of view, but it doesn't, like why as a specific extra term is not clear. Okay? So let's at this point, it's actually useful to also ignore all the neural network aspects of the problem. Okay, we are just thinking in terms of like random variables, and so what is our model? Our model is going to be, we're going to have two random variables, x and z. X is z is the latent random variable, x is the observed random variable, like an image or something. And what we want to estimate is some parameter of the joint distribution. Okay, so let's say theta star is the parameter of this joint distribution. Okay, joint distribution of x and z. So p of x comma z, I didn't actually write it here, but p of x comma z is going to be the joint distribution, right? So that will be parameterized by some theta star, and that's what we want to estimate from data. So the data is only x is the only thing we observe. We want to estimate theta star. Okay, and if we somehow did that, then if you know theta star, then you can sample from. That means we know what P of Z is, because P of theta star, if you know theta star, which is parameters of the joint distribution, you can average out x's and you get P of Z, right? So that's you can do. You sample from P of Z, some sample, let's say it's called Z of I, and then again use my conditional probability distribution, because if I know the joint distribution, I can compute all sorts of things, conditional probability as well. So compute the conditional probability of x given Z and sample from that. Okay? That's what you would do in an ideal case. Okay. But as I said, as we defined in the previous slide, it's a little bit not fully specified in the previous slide, because we only observe x and we're not saying anything about the latent random variable. Okay, so we have to say, we have to kind of restrict it to something, so that we actually have a reasonable, we actually can learn some theta. Okay, so we'll assume that P of Z is going to be Gaussian. Okay? So P of Z is going to be a Gaussian distribution. So this is what you're going to assume. So P theta star of Z basically is a Gaussian distribution. And what we want to do is learn still theta star, same thing as from the previous slide. And how do we learn that? We can learn that by saying, okay, P of theta star is the actual thing that maybe that was the data generating parameter, but we know that P of theta of x is nothing but the joint distribution, which is factorized this way, and average out Z, just marginalize out Z, right? So it's just getting rid of Z. So we know that this is the probability mass on the data on any for any given X, and this is literally the likelihood of the data, right? So the likelihood of a specific X. If you want to maximize the likelihood, you take p theta of x1, x2, x3, x4, maybe several such values. For every theta, there will be a bunch of these numbers. Maybe you maximize the likelihood over that data set. Okay, but you can see that if I want to maximize the likelihood, I have this integration that I need to do. Okay, in this model. And typically, when you introduce latent random variables like Z, this problem should become easier. And that's what we saw. For example, if you maybe not in this course, some of you have done Gaussian mixture models in 575 or 572 in the program. Gaussian mixture models, the whole point of having some latent random variables in the Gaussian mixture model is that it makes the likelihood maximization instead of, if you naively maximize the likelihood, you can't do it. But if you explicitly talk about explicitly have latent random variables, then you can actually maximize not the likelihood, but some proxy of the likelihood easily. Okay, so it's very similar to that. Ideally, okay, my point is that if you have Z, the whole point of introducing latent random variables is that you should make the problem simpler. But here we introduce Z, but the problem is still complex. Okay, complex in the sense that there's still an integration which we are not able to get around, and that's where we will use approximation. Okay, approximation or variational approximation, it's called. Okay, so what are we going to approximate? We already said by definition P of Z is Gaussian, so there's nothing to do there. But what we're going to approximate is P of not this, but P of Z given X. Okay, so we say, okay, where is the P of Z given X here? It's not there, right? But you know that if I had this term, I can always use again base rule or some basically the this decomposition of joint distribution is equal to P of Z given X times P of X also, and so I can replace this with a term which involves Z given X, and that's the one I'm going to approximate. Okay. We'll see how why that's the case. Yeah. So we'll come back to that hard problem. This hard problem is what's leading to approximation approximation of not exactly this, but P of Z given X. Okay. So now let's actually look at the architecture again before we get back to that thing that we want to approximate. And remember why we want to approximate? Because we want to maximize likelihood, and that's hard. Okay, there's an integration term there. So let's look at the architecture again. If you have Z, okay, if I have Z, then there's a P of X given Z that is captured by the decoder. Okay, I'm trying to map it back to our architecture. So if we have Z, then we can get a X given Z through the decoder. And as I said, the decoder is not predicting the X itself. It's going to predict the mean of X and conditional mean of X and conditional variance of X. And then you can use them as parameters of your normal distribution and actually get an X. Okay. So then therefore the theta basically represents the parameters of the decoder. Okay. It doesn't have a neural network, but will be a neural network mostly. But anything here. So going from Z to X is via this process. So you compute the mean and covariance and then sample from it. Okay. So this is how we're going to set it up. And so we're making an assumption here, right? So there's a normal distribution on the output space also, but it's conditionally normal. And as I said, and Z is going to be Gaussian distributed. Okay. So we know the distribution of Z. If we have Z, we know what the distribution of X is because it's literally just go through the decoder of the given parameter, whatever the parameter is, and get the mean and covariance, and then just get a sample. So we know this conditional probability. Okay. We know this, and we know the distribution of Z. Now, what we want to do is because of that integration term in the previous slide, we're going to approximate the probability of z given x, okay, using an approximation called q of z given x. Okay, so this is an approximation, variational approximation of the original p of z given x. Okay, this is not z given x. Okay, all I'm saying is there's a John distribution in x and z. Okay, there's some true parameters. P of x has this equal to some integration of averaging or z effect, but that's hard to do. So we're going to approximate something about this John distribution of over x and z, and that something is going to be an approximation of z given x. Okay, how are we going to do that? So z given x means I have to start with x, I have to get some z, right? And this is exactly what we saw in the encoder part. Start with an x, produce the mean and the covariance parameters, put the parameters of normal distribution, and sample a z. Okay, so this encoder, the whole encoder side is basically an approximation to a specific conditional probability of z given x in our generative model. Okay, the whole encoder side is just an approximation to that. Okay, any questions here? Yeah, we'll be updating this parameter and this parameter, but remember, so there's no need to think in terms of backpropagation and neural networks at this point. I mean, we discussed that 2 slides ago. Now we want to really think in terms of graphical model, what's going on. And what's going on is pretty much, if you didn't want to look at the next slide, all I'm saying is there is some joint distribution of x and z where I want the marginal distribution over z to be Gaussian. Okay, that's literally pretty much specifying my joint distribution with some constraint, right? It's the Gaussianity constraint on the marginal. Given that, I know that the likelihood of my data, not the given that, in general, likelihood of the data is just by definition this. Okay, in which I know this, I already specified that as a my assumption in my model. It's just that I don't know this, but this, okay, I can flip, I can flip. So I don't know this, but this is actually captured by the decoder, right? But I still need to integrate over z. So this, to get rid of this integration, I will have to deal with the probability of z given x also. Okay. So all I'm saying is this we have already assumed. This is the part of the decoder. To deal with this integration, we need to look at the probability of z given x also. Okay. And the probability of z given x is just an approximated using that q of z given x, okay, which is going to be an encoder network. But the network part is not relevant. So the model itself, this is the original model. The joint distribution is literally there's only 2 random variables involved. Okay, but because we can't do this integration, we'll have to approximate something about this joint distribution. We already are approximating this using a decoder network. We already assuming this to be Gaussian. There's one more thing that we need to kind of specify so that we can actually deal with this integration process. Yeah. What do we need to specify is the conditional probability of z, conditional probability of z given x. Okay, that we specify using a encoder network. Okay, that's all seems hand wavy, but you can actually derive it, and I know we will. So we'll derive it in the next 2 slides. There'll be a lot of equations, but bear with me. But it's just what we did in the previous couple of slides is like more intuition of like what's going on in this model, right? I said like integration is hard, and that's why we want to bring in an extra approximation. But it just algebraically comes out also, okay? By just writing the likelihood expression and then just doing some manipulation. Okay, we'll see that manipulation in the next slide. But before that, I want to quickly point out a definition, which is these are definitions that basically we only care about one last thing, which is the definition of what is called a KL divergence. Okay, it's a measure of distance between. It's not really a distance metric, but it's a measure of similarity between 2 distributions. Okay, it's a measure of similarity between 2 distributions, which has this expression. Okay, so it's just a KL divergence between a distribution P and a Q. Let's say P and Q are discrete distributions, as in the probability mass functions for simplicity for now. Then the divergence or some sort of dissimilarity between them is the sum of the probability of x, P of x, times the log of P of x divided by Q of x. So P and Q are exactly the same. Okay. Then the scale divergence is going to be 0. Okay, log of 1 is 0. Okay. If they are different, if P and Q are different, then this term is going to be a large positive number. Okay. And this just trying to kind of map it with, you can define scale divergence in terms of entropies as well. So you can see that there's a sum of P log P here, and so there's a negative sum of P log P here. And so if you've heard of this term called entropy, I don't know if you've done decision trees, the impurity measure of a node from which you kind of split, right? There's Gini index and entropy and various things. So this is the definition of the entropy, that you would have used. So entropy and scale divergence are very similar to each other. Okay, and actually very much related. And entropy and scale divergence are also related to, I guess, the notion of information. Okay, how do you mathematize the notion of information? Is by saying, okay, the information in a specific outcome is denoted as negative log of p of x. So if the outcome is low probability, then log of the low probability, like a very small value close to 0, is going to be a large negative number. Okay, log of let's say 0.1 is a large negative number, and so negative of that is like that large positive number. So if the outcome is very less likely, then the information contained in this outcome is high. Okay, that's just the interpretation of this. Okay? And if the and similarly, same thing with entropy, right? If, for example, your distribution, your x is a fair coin toss, then the entropy is going to be the highest. If it, you don't know the outcome, both outcomes are equally likely, entropy is going to be heads. But if you already know that your coin is completely biased, like most of the times, in fact, all the time it's going to just land heads, then there's no surprise in the outcome anymore. So your entropy is going to be 0. Why is that? Because p of x, one of them is only 1 log 1, and the other term will be 0 log 0, which by definition is going to be, we're going to say it's 0. Okay. Although there's going to be 0 log 0 is 0 times minus infinity, but let's say it's 0. Okay. So entropy is 0 and there's no surprise in the outcome, and that's how they're defined. Okay. So actually, on this slide, let me go to the last slide first and then come back to the slide number 38. So this is just showing scale divergence between two distributions, okay, P and Q. So let's just focus on this thing. Ignore that right side, okay. They ignore the right side is just showing something else. So scale divergence in P and Q. So P is here, this bimodal distribution, and Q is here, like a unimodal distribution. It's just showing, sorry, Q star. So which, if you want to find, so okay, let me set the context properly here instead of directly describing the graph. So basically, what we're trying to do here is showing what is the, let's say there's an original distribution P, and I want to approximate the distribution using some other distribution. Let's say I can only fit Gaussian. I can only fit some mean and variance, and so I know that my approximating family of distributions is going to be Gaussian, irrespective of what the original distribution is. Let's say the original distribution is this bimodal distribution. Okay. Obviously, if you have a bimodal distribution, Gaussian distribution, there's no best Gaussian. I mean, there's no perfectly, fit to that, right? So unless you have two Gaussians and you can have a mixture of Gaussians, you can't fit it. Okay. But if you in this figure on the left side, we're just showing if you have a scale divergence and if you find the best Gaussian fit to the P, then that's going to be this Q star, which is going to look like this. Okay. Okay. So what's the difference between the left figure and the right figure? Is that the scale divergence term, where does P appear and where does Q appear? Is the only difference. Okay. In the right figure, the Q is in the first argument instead rather than the second argument. Okay. If Q is in the first argument, we are still doing the same. We want to fit a Gaussian, which is approximating the original input distribution, which is the two bimodal blue thing. Then if Q is in the numerator, okay, or is the first argument basically, then the best approximation is actually this dash green curve, which is different from this side. Okay. So I guess one basic thing that you can take away from these two graphs is that depending on whether this distance, this not really distance, this dissimilarity measure between the scale divergence, the similarity measure is not symmetric. You can't just flip the arguments and expect the same outcome. Okay, it's not a distance measure. Okay? Distance is a symmetric, should be a symmetric function. This is not a distance metric. And here this is just showing what the best approximation from your approximating family would be, depending on where where Q is. Okay. Any questions here? Or is this too complicated? It is complicated, but nonetheless, basically the takeaway from this slide is just that it's not symmetric. Okay. Now let's come back to slide 32, 36. Sorry. All I want to say is that you can't just flip them, because if you flip them, if you flip to Q, then there'll be Q log Q divided by P, which is different from P log P divided by Q. Right? So it's not symmetric function. But anyway, I just want to define this because in our attempt to kind of deal with this maximizing the likelihood of the data, we will deal with this integration problem. Because the integration problem, we're going to do an approximation. And because we'll do an approximation, there's going to be basically the scale term as a second term in addition to the reconstruction term. Okay. Few slides ago, we just motivated it directly, right? The moment we said, okay, X and Z are random variables, let's just add an extra regularization, extra term, on the latent space, just like the reconstruction around the output space, we're going to have an extra term in latent space, and it's just going to be some distance measure between distributions. We just said that at the very beginning, but now we're going to see how it's done. So this is going to be kind of, I want to do it just to show you algebraic manipulations, but it's not really important to memorize or anything like that. Just to show you that this is a very principled way to get to an objective function. Okay, so what's our struggle right now is that the maximum likelihood objective is not nice in our problem, which has two random variables X and Z. The MLE problem, which is basically let's make everything log. It's not just likelihood, but log likelihood. So the log likelihood of the data is just very hard to optimize for. Ideally, we just want to maximize the log likelihood of the data over the parameters of our graphical model, right? But it's just that it's hard to do. So then we'll take a bunch of steps to kind of make that objective into a form which is actually optimizable. Okay. So how do we do that? So first step is just to average out this log likelihood of the data with respect to Z. Okay. Why can you do that? Because this term has nothing to do with Z. There is no Z here. I mean, there's only X and there is theta. There is no explicit Z random variable. So you can always take an expectation with respect to an unrelated random variable by definition. Okay, so we just took an expectation with respect to Z. Okay, now this is where we introduce this approximating distribution Q of Z given X. Okay, this variational approximation we've already introduced because we said, okay, we'll take expectation with respect to Z, but what is the distribution over Z? We're going to take this approximating distribution. Okay, that is just, there is nothing going on here at all. Then what we'll do is, okay, now let's ignore that part. I mean, let's keep it there, but let's not focus on it. Now this P likelihood of the data, just because of Bayes' rule, or just the definition of conditional probability, is just going to be joint probability divided by conditional probability, right? That's again nothing new here. So here, what we want to do is, remember previously when we wrote the likelihood function, there was an integration. Instead, this time when we're just writing likelihood function to have no integration yet. Okay, and we see that okay, we didn't write it in terms of integration, but then we still have P of X given Z. That's still okay. We have a decoder which does that, Z to X. This is the decoder part which can deal with it. P of Z, that's also fine. We assume that P of Z is Gaussian, so that's also good. But this is, we don't know how to get, because the decoder doesn't give us this. Okay, this is what we're approximating. Okay, so either you could do the integration, or that integration effort is hidden in this conditional probability P of Z given X. Okay, so because we don't have, so we can't get around integration. Okay, if you want to, although we just use base rule or allow the conditional probability definitions, you still have integration here if you want to write it in terms of these guys. Okay, so integration we can't get rid of, and that's why we get trying to kind of approximate or just proxy it with some other approximating distribution, conditional distribution. Okay, so what is the approximating distribution? Is the P of so Q of the given X. Just multiply and divide by the same term. That's just again algebraic manipulation, just nothing going on. And then what we do is we're going to collect terms together. We're going to collect terms together, by which I just mean like we're going to pair. Okay, let's take this with this, and this with this, and so on. Okay, we'll just show you in the next slide. So basically, let's extract out this term separately. Okay, P of X given Z. So this we have a handle on because we have a decoder. And let's also collect Q of Z given X with respect to and then P of Z. So why did this come in the denominator? Because we put a negative sign. Okay, everything is in a log. So if I put a negative sign in the log, I can flip the terms. Okay, so pick these two terms and flip them. This will become a numerator. This will become a denominator. Okay, then the only thing remaining is these two terms. P of Z given X, and again this of Z given X. Okay, so all we did so far is just manipulation, right? So we just introduced some numerator and denominator, which is the same thing, and these two are the same thing, and just we separated our terms like this and this here, and the numerator here, and this denominator here. Okay, and the minus sign just so that you bring the PP time to denominator. Everything is log. So now here's the so far we have not done anything. We still have an integration issue because we still have this term which we don't have a handle. Okay, but that's where the cool thing happens. First, I mean, we'll just rewrite it into definitions. Okay, this expression turns out that, remember, Z was distributed according to Q of Z given X. Okay, so therefore this becomes the KL divergence between Q and this distribution that we assumed. Okay, just by definition, because Z is actually with respect to Q, so expectation, remember, is just the sum over probability of that random variable, right? So so it just becomes the KL divergence this term. Similarly, this term also becomes the KL divergence with these two arguments. Okay, just that's why we introduced the KL divergence in the previous slide, just so that we have the definition so that this happens. Now, so we did all this manipulation. What we have to get rid of is this P of Z given X, which we don't have. Okay. And Q of Z given X, we do have because we have an input. Okay. So we can do something. So the way we'll do it is that's pretty much the derivation and the manipulation that we want to do. And where we're going here is we want to get to the objective function. Remember, there's a reconstruction error and some latent loss function, latent loss term. And the way we do it is actually look at this object, look at these three terms that we generated in the previous slide. Okay. And we know that each of these terms, like KL divergence especially, is non-negative. Okay, that's just a property of this dissimilarity measure, that it's 0 when both distributions are the same, and the moment the two distributions are different, it's non-negative. Okay, so we know that this term is non-negative, and there is a term that we say there is a conditional probability that we don't know how to deal with it, so we can just drop it. Okay, when we drop it, then we are lower bounding the likelihood function of the data. Okay, remember in the previous slide we saw likelihood data is equal to these three terms. We know that this term is positive always. We drop it. That means the likelihood is greater than or equal to these two terms. Okay. So by dropping that last term, we just got rid of the pesky integration. Okay. I mean, it was not easy to just drop it. We had to bring in this approximating distribution. Okay. We dropped the hard part and we got something else, which is an approximating distribution. Okay. And those two terms together are therefore the loss function. Okay? This term is called the reconstruction error. This term is called the KL divergence, I guess. latent space loss function. And in fact, this whole thing, these two terms together, also are called the evidence lower bound. Okay, ELBO. I don't know if you've heard of this term, but it's called the variational lower bound and evidence lower bound. It's basically lower bounding the log likelihood of the data. Okay, and so instead of maximizing the likelihood of the data, we can now maximize the lower bound on the log likelihood of the data. Okay, and this term we can actually work with because this is just a decoder, this is an encoder, and this we already assumed to be Gaussian. So everything here, okay, is not hard for us to evaluate and therefore compute gradients and therefore maximize. Okay, so any questions here? So this is the, I guess, more principal way to get to those two terms in the variational autoencoder objective. Okay, what is the time? Let's just wrap up VAE. So we've seen this figure like several times. So the architecture again is basically captured by this figure here. Basically, you're going from image through a con, basically a con type of operation to a, the mean vector and the variance vector, and then from which you can get a sample, from which you're again doing a decon operation to get to a mean tensor and a covariance tensor basically, and then from which you're getting a sample, and that's your image. So that's completely explicitly drawn out to be mu of z given x. So this is like a specific notation here to capture that, and standard deviation vector of z given x instead of like the whole covariance matrix instead of that. And then you get z by sample. You get the mean, the covariance vectors, or mean and the standard deviation vectors, and then again use them as parameters of the normal distribution and get a sample of x. Okay, so that's the network, and you can optimize even though there's sampling going on in between. While training, you don't need a sample. Okay, while training, you can just compare the mean vector with the input image to CEO, how different they are, and that literally gives you the squared loss, because Gaussians, if you compare the mean with a sample, you basically get a square loss term. Okay, if you take the log, remember Gaussian distribution has an e to the power minus x minus mean of x the whole square, right? So if you have a data point, and remember all analysis, our evidence lower bound was the log likelihood, was for the log likelihood. So log likelihood, you just get a square loss term, and that's the first reconstruction term. Okay. Anyway, after doing all that work in training, once you have the decoded network nicely trained, you can, if you just want to care about generating samples, then you can just focus on the decoder, start with the Gaussian distribution. Remember, this is just by the assumption of our VAE. Start with the Gaussian sample, pass it through, and generate a new data point. Okay. And this is the paper, auto-encoding variational base in a top conference in machine learning. One of the popular conferences in machine learning. And here are some figures. So this is something that you could not do with just autoencoder. Okay, so there are three figures of three different data sets actually. So this is a figure from an actual paper from around that time, just generating new cases. Basically, it's not very high quality as of you see today in 2023, but at that time doing this was not trivial. Was not easy. Similarly, for even part-time, you can generate the 32 cross 32 pixel images, but it's just, I mean, if you actually look at it, zoom in and see, it's not that good. But you can generate new images for each of the classes. And here, actually, you can see an interesting thing, which is not possible, as I said, with autoencoder, is the idea that if you're in the Z space, remember there was a Gaussian distribution over there. But instead of sampling, what you could do is, okay, I'm going to start with some starting point of Z's, and in particular for this MNIST data, our Z dimension, our Z data, whatever the Z vector, sorry, let's say it's 2-dimensional, or even if there are more dimensions, just focus on two of the coordinates. Okay, and what we're doing is varying Z1 and Z2. So basically, we're doing a grid computation. Like for every Z1 and Z2, let's see what the output mean image looks like. Okay, just passing to the decoder. So basically, think of this. It's like here, for example, think of this point as when Z1 and Z2 is 0, 0. What's the mean image that I'm getting? And then as I change Z1, and keep Z2, sorry, at the chain Z2 and keep Z1 the same, then this is how my images are, mean images are changing. Okay, so you can see I'm going from like a 7 to 8 to maybe something looks like 9. And then from here, if I keep Z1, Z2 the same, but change Z2, so change Z1, then it's going from 0 to 3. So there's an interpolation of like how these things are spread out in the lower dimensional space, and they have a better structure than if you just look at where the points are embedded in the using an autoencoder. Okay. Any questions? I think this is pretty much last. We'll take a break for 10 minutes and resume at 5:13. Okay. Okay, what I want to do before talking about GANs, before we start discussing GANs, is to just recap, not really recap, but like show two more links basically. This is from that paper, the ICLR 2014 paper, autoencoding variation base. This is the one which started this, I guess, restart this area. And we did not discuss anything about the training process. Obviously, if you have a neural network, then the training process is just going to be gradient based. But there are other approaches like EM, for example. EM is a technique for learning the parameters of a Gaussian mixture model. So similarly, you could do, there are ways to just work with probability distributions and not really talk about neural networks if you want. Okay, so that's called variation inference, stochastic variation inference, for example. But let's actually look at an image from that paper, just to kind of, this pretty much summarizes what we talked about VAEs. But in terms of the notation, this is the notation that we've seen when we talked about naive-Bayes, for example, naive-Bayes model, late initial allocation. They all have similar symbols. Okay, so this is called a late notation, where this, this rectangular box just means that that thing is happening n times. So that's why there's an n there. So there's an n data points, for example, or n images. And z, which is not shaded, is a hidden random variable. X, which is shaded, is a observed random variable. Okay, and so those are the only two random variables, and those two random variables are related to each other through a joint distribution, some joint distribution. And the joint distribution has a parameter theta. Okay, where we assume that the distribution of z is Gaussian. Okay, but the problem is we can't learn theta easily by just maximizing the likelihood of the data. Okay, and so what we do is say, okay, we're gonna do a variation approximation of the distribution of z given x. Okay, this dashed arrow, and that dashed arrow, which is the conditional probability of z given x, has some parameter phi. Okay, so we're gonna learn phi and theta now. That's the whole twist. So we can't directly maximize the likelihood because there will be some intractable quantity there, which is the conditional probability of z given x. We're going to approximate that using a q of z given x, which is this dash arrow, and then we have its own parameter p. That's the approximation. The dashed arrows are the approximation. If you remove the dashed arrows, that's the graphical model. There are two random variables. One is observed, one is not observed. And there is the things outside the box, by the way, are generally not random variables. So things without a circle around them are just parameters to be learned. Okay. And generally in the graphical model, without the variance approximation, these dash things will not be there. So nothing here. It's just a box with two random variables and a parameter outside. Okay. So So you need to kind of understand this layer by layer, right? So what is the original graphical model, and then see what is the approximation happening. So this image is a good representation there. So any questions here with this image? No questions? I think there's a full course and actually a huge book by Professor forget her name. It's called Graphical Models, I guess. It's like a 500+ page book. I think there's a link in the syllabus to that book, perhaps. So there's a full-fledged course if you want to just understand how graphical models work and what they encode and so on. But let's actually skip to our one last thing, which is a link on our learning goals page, which just links to, I guess, PyTorch repository. We've been using PyTorch quite a bit in this course. So in the examples folder, there's actually a bunch of examples in this examples folder. You can see ImageNet or MNIST or just regression, reinforcement learning that we'll talk about in the next lectures. So there's a lot of examples. One of the examples is called a VAE, and there's also something called Vision Transformer, which is a interesting application of transformer technology to images. But in the VAE, it's a nice example for basically compressing MNIST data. So most of these examples actually work with reasonably small data sets so that you can really appreciate the model rather than like getting the complexities of training these things. So I'm in the VA folder, so I just opened it in a different tab. So this is a script. I mean, it's very similar to every other script that we've seen in this course. There's a bunch of so instead of doing it in Colab, for example, if you want to do it on command line, sometimes you want to just pass command line arguments. So this is how you do it. Like, what is the batch size? If you pass ---- dash batch size, you don't have to edit it in the code every time, right? So I don't know how this came here. Let's stop it. So there's some parsing going on, but I want to just focus on the definition of the model. Okay, so you can see what the model is. So firstly, when you instantiate, things are not tied together. So a bunch of fully connected layers. So FC1, FC21, FC22, these belong to the encoder, and FC3 and FC4 belong to the decoder. Okay, in this VAE definition. So what did the encoder do? Where did they get this 784 from? Remember, MNIST has 28 pixels plus 28 pixels. That's 784 numbers. Okay, so that's where. So there's 784 as the input size, input dimension, and then they're saying they want to go down to 400 dimensions. Okay. So one I guess fully connected layer, and then in 400 dimensions they want to produce two 20-dimensional vectors. Okay, that clearly is a 20-dimensional mean vector and a 20-dimensional standard deviation vector. Okay? And then that's on the encoder side, and then the decoder takes in a 20-dimensional vector, like a sample from a normal distribution to these two vectors, goes to 400 dimensions, and again goes back to the output space, which is 784 dimensions. Okay? And then you're comparing the reconstruction error between this 784 dimensional vector, or basically 28 × 28 black and white image, and 28 × 28 black and white image. And then in the 20-dimensional space, you have the KL dimensions last term also. Okay, so that's the model definition. You can see that instead of an explicit dot forward, there's an encoder which produces the mean and the standard deviation. There's a sampling process, that is the reparameterization step, which is just this random here is the sampling, sampling from a normal distribution. Okay, and then decode, as I said, like there is a fully connected layer going into 400 dimensions again, going back to the 28 × 28 or 784 dimensions. And they have explicitly used ReLU also in that two fully connected layers. There's a ReLU operation in between. Okay, and the forward pass is to first encode, then sample, and then decode, and they're also returning the mean and the variance. Okay, in fact, it's not the it's another thing. Variance standard deviations are generally supposed to be positive. Okay, how do you ensure that whatever the neural network is producing is always positive, right? You don't, right? So the way you think about this is that whatever neural network produces, we're going to call it the logarithm of the standard deviation. Okay, because log of standard deviation can be any number between minus and infinity. Okay, whereas the log's argument has to be positive. So you assume that whatever numerator produces is the logarithm of the standard deviation, and then e to the power of that would be always a positive number. Okay, yeah, it's an interesting trick to kind of ensure that you don't produce negative standard deviation numbers. Okay. Any questions? So, and they have to obviously define an extra. They have to define their own loss function, because it's not just the cross entropy loss, which is a reconstruction error generally. Think of this as, instead of just cross entropy, it could be the squared mean square error. Okay, just the squared loss. But they also have this KL divergence. It just turns out that if you have Gaussian distributions, that very crazy looking DKL of something with respect to something else actually just turns out to be just a function of the parameters of the distribution. Okay, so it's just a mu and the log var, the two things that you computed at the encoding step, and that's it. But basically, just those determine your reconstruction error. Because remember, one of the distributions is just a normal standard Gaussian, so mean zero and a covariance or identity matrix. So there's no parameters there. The only thing that's there is this Q of z given x, and that's parameterized by the mean mu and sigma, right? So those two. So any questions? So I would say, if you're interested in VAEs, and VAEs have a huge application, at least people are trying to have been using it for anomaly detection. So at least as a starting point, because they can model the data, compress the data into low dimensions and so on. And so if you have an anomalous data point, they will be far away in that in the lower dimensional space. So there'll be an anomalous z hat or whatever. So that way you basically by anomaly you're just seeing something which is far away, or something which is not in the z space, doesn't look like as if it came from a Gaussian. Okay, that's a simple way to think about it. And so a lot of papers in various different applications, various different engineering disciplines and whatnot have been using VAE for anomaly detection. So it's worth playing around with this. Any questions here before we switch? Yeah.
In the decoder, why is there only like one line for the main parameters in the VAE?
Oh, here. Oh, in the decoder, there's only. Yeah, this is the VAE. Yeah. Yeah. Here they did not create the two. Here we did not create the two mean and the standard deviation vector on the decoders. For training, it's actually not. What we saw in the paper, or at least in the slides, was that there should be a mean and also another similar size vector. So there is no, they removed the sampling on the output side. So, which is not correct, but so you can think of this as the mean. So if you remove the sampling, you can just say, okay, what I'm outputting on the decoder side is just the mean of my normal distribution, and I'm just gonna, instead of sampling, I'm just gonna say the mean is the output. Okay, that makes sense for training, because when training you don't need to sample, because you can just use the mean. But yeah, in the slides and everywhere else, we have explicitly said there should be a mean and a covariance, and you sample from that. Okay, so now let's switch to GANs. I just wanted to again just quickly recap the images. I think we saw this guy, which is drag your GAN from this year's some conference. These are all, I guess, latest innovations on this. So here, here's the application. Mostly creative usage. This is the origin. This is the paper link also. And then the next one was to kind of compete with these text-to-image models like DALI 2 or 3 or stable diffusion type of models and so on. So that also you basically give a text like a golden luxury motorcycle, and then you actually get a motorcycle image. Okay, so those are the two applications that kind of motivate, like why also look at GANs. There's actually some older links on our lecture goals page. So this is from 2023 years ago, and here they're showing how to. They have their. There's so many papers on GAN. So this paper is talking about creates a creates a full image given some outline, basically. Okay, so given, I guess the initial outline was the thing that you saw here, and given this outline, it transformed to that final image. I think you saw this. Yeah. So this is just a link from our lecture goals page. You can look at it. But there are many variations that you can do once you understand the idea of how to generate something new. Yeah. And obviously, ethics should not be missed. It's important. What is the training data used to train these models is important. Okay. And on our page, there's also a link to, on our lecture goals page, there's also a link to a GAN called DC GAN. Actually, the DC stands for literally decon operation, the transpose convolution operation we were talking about. So this is an example of, I guess this is training images. At some point, there's going to be an example of like output images. It's going on. Yeah, so for example, these, I mean, they're not perfect faces. You can see a lot of deformities and a lot of issues, but this is a tutorial from literally ByteDance's website, beginner tutorial. So you should, if you're interested in this direction, you should try it out. Okay. There's no explicit assignment. I could have made an assignment for this, but I'm just saying that these are the helper, starting codes to try out, and these are just tutorials. We're not trying to do anything complex. Okay, with that these are types of things we can do. Let's actually come back to our slides and talk about GANs. We only have 30 minutes. So I'm not going to rush through. Actually, GANs are not complicated, but we might kind of ignore some minor details. Okay. So remember, our purpose is still to create some object from which, if we give a source of randomness, we can generate a new image. Okay. Ideally, a new image, not some lookup from a database. So what is the idea? So the idea is going to be ignore all the maximum likelihood, all sorts of statistical perspectives. And what we're going to do is think in terms of a game theoretic perspective. Okay. Now, I don't know if has anybody done a course on game theory? No. So you've done a course on game. Great. So it's fine. I mean, game theoretic perspective just means that you have to kind of think in terms of players. Okay. If you played a two-player game, let's say chess or something else, then you know how a game works. So game theory is a branch of, I guess, applied mathematics, which kind of just studies what's the best strategy for each player. If each player plays, rationally or whatever, optimally, then what is the outcome of such a game? Things like that. Okay, that's just some analysis, mostly analysis, and there's also some prescriptive parts to that field. But so we're gonna get inspiration from that and design a basically some sort of a setup where we'll still do gradient descent and all that on our network parameters. And in fact, our networks will be CNNs and the transpose of CNN type of blocks. But the objective function is inspired from this game theoretic angle. Okay. So let's see what the game theoretic angle is. So basically, first you want to think in terms of two scenarios. What is the game? There's going to be a game between two networks, essentially, or two objects. And in fact, those two objects, but in our case, it's going to be neural networks. Okay? So basically, there are two networks, so therefore there are two players, and the both players are part of a game where one player, let's call it D. Okay, it's going to be the word. I guess the symbol D represents essentially a decoder network, if you want to call it that. Basically, it's a player in a game where if it is given sample from real data sets, then it should say, okay, this is the real data set. And so for real data set, it should output a number which is close to 1. Okay. Just think of D as a binary classifier. If the real data set, it should say, okay, it is a real data set. And if it's not a real data set, sorry, real input, real image, as in an image from my training data, it should say 1. If it's not an image from my training data, it should say 0. Okay, that's the action that this player takes. Okay. And in the second scenario, now we involve the second player, which is the player G, whose objective is to confuse this first player. Okay. Remember, the first player is just trying to say, okay, hey, this is an image from a data set. This is not an image from a data set. Okay, that's what they should be doing. And the second player G, their objective is to create images so that the first player is confused. How do you create images? Ideally, I mean, obviously, if you have access to the training data, you just literally give the training data as input, but then then you haven't done anything. You haven't confused the first player D, because D knows that, okay, if this is training data, I should output 1. Okay, they'll output 1. But what should G do? G should somehow, use noise, starting point, some randomization, create a image, and when that image is passed to D, D should be confused. As in, D should say, okay, this is not real data. So G should try to say, okay, this is not real data. Should we try to make it close to 0? Whereas G should try to improve its process so that D will try to will give it a score of 1. Okay? So basically, this is the game between two players, D and G, where D is trying to discriminate between real images and synthetic images or generated images. And G's objective is to create better and better generated images so that D doesn't do its job well. Okay, so that's the objective. So let's say G produces some output X. Okay, let's say images, but let's say G produces some output X, and D takes an X, any X, and produces value between 0 to 1 or 0 and 1 explicitly. Okay, so remember from the previous slide, I said D should, if X is from real data, then D should be giving values close to 1, and X is not from real data, then D should be saying it's 0. It's just a binary classifier. And G should be producing X's, which confuse D to be not doing that. So if you think in terms of one-dimensional space, let's say my real data is just black dots. Okay, real data is black dots, and my G is producing data whose distribution looks like the green curve. Okay, now imagine the black dots and the green curve are far away from each other, like they don't overlap. Okay, then you can really think of a very simple binary classifier, right? If black points are far away from the green points, then you can have a threshold and saying, hey, if you're lesser than the threshold, it's most likely real data. If you're greater than the threshold, you are most likely synthetic data. So what we're trying to do is train the parameters of the G, or whatever, change the parameters of G such that this green curve overlaps more and more with this true data. Okay, but when doing so, G itself directly doesn't have access to the true data. It's not like you're doing maximum likelihood. It's not like you're fitting the parameter of G by saying, okay, maximize this such that we are fitting as much of input data as possible. It's not. It's a little bit indirect. That G's parameters are being trained such that indirectly it's getting feedback of how much is confusing D. Okay, so that's I guess the departure from just maximizing likelihood of data and training parameters. Okay, so here you can see that if both of them perfectly overlap, D is not able to kind of distinguish. Like here, D at least has some, here it's saying, okay, this should be data. Here it's saying it should be synthetic, but in between it's saying, okay, there's some space where it doesn't know whether it's synthetic data or real data. Okay, so this slide is just saying the same thing what I just said. So discriminator, or one of the players in this game, discriminator network, therefore it's a neural network. All it's trying to say is that if it's real images, it's real, and if it's fake or synthetic or generated images, it's fake. Okay, and the generator network, the second player, their objective is to create realistic images so that the discriminator is fooled, as when discriminator produces the opposite answer. Okay, or doesn't produce the right answer. What's it?
What's the purpose?
So these two are players, right? They are trying to play. They are trying to play better and better. So which means that they're trying to learn their parameters better and better. After through this play, both these players' parameters improve, or their playing strategies improve. Eventually, we can stop the game and then just look at the generator. Their parameters will be well tuned such that now we can think of this as the way to generate new images and drop this whole extra game business and the first player and so on. Okay, so now you have this object from which you give a random source. It's going to produce realistic images. It's just that to train this parameter, there is no directly some cross entropy laws or some maximum likelihood thing that we saw in VAE. It's indirectly getting feedback, but if it doesn't produce the right, it knows that it's not producing the right answers, because if it's not producing good images, then discriminator will produce 0, and it doesn't want that. So we have to improve its parameters such that we don't get zeros here, we get ones. And when we train discriminators, we have this we know this is from training data, and anything else we know that it should be. It's basically a binary classification problem for this. Okay. But the purpose is just to get a better tuned generator network and the discriminator network we don't care. Generator network we can actually sample new images. Okay, that's what the drag again and stuff that you saw, which seems very impressive. That's basically the starting principle. Okay, so it may seem very convoluted, but we just this is a way to kind of not directly model a distribution. Okay, this is, remember, there's an implicit approach. So again, like this is like the third time showing the same picture, but basically generator produces a sample, let's call it G of Z, and basically discriminator wants to say X is 1 and G of Z is 0 or whatever, real and fake, and G should tune itself such that discriminator, when it acts on G of Z, is also producing the same output as it's producing for D of X. Okay. So how is information? So this is the actual data that we have, and we are training this guy and this guy. Okay. The feedback is coming in a very indirect way to the generator to start tuning its parameters, so that it improves. It's able to confuse the discriminator. So although the setup is game theoretic, there are two players trying to compete with each other. One is trying to discriminate better. The other one is trying to fool the discriminator through that competitive game, because it is against each other. Okay, it's not like they're cooperatively doing something. It's a non-cooperative game. But while learning to improve their strategies and improve themselves, one wants to discriminate better, one wants to generate better images. Through that non-cooperative game process, then you get a good set of parameters for this and good set of parameters for that. We don't care about that for generation. We care about this for the generation. Any questions here? Okay, let me actually let me actually skip those 3 slides because it's summarized in these 3 slides, which is what I want to go over. Like now, let's talk about the actual game process or the training process. Okay, because the training process is set up as a game rather than some maximal likelihood objective. Okay, so what do? We create a mini batch of real data. So we start with some current parameters, right? So it's an iterative process, very similar to gradient descent. You do a forward pass and do a backward pass, and forward pass and then do a gradient update, right? So here we get a batch. So in the regular case, we know we got a batch, we did a forward pass with a gradient update. Here we're going to get a batch of real data and get a batch of synthetic data or whatever generated data from the current parameters. And we need to improve both of them. We need to do a gradient update on both of them. Okay. For the real data and the generated data, we can score the discriminator, because for real data, the label is real, and for the synthetic data, the label is synthetic. So it's a binary class. Binary, you have a batch of the combined data where we know that for some images our label is true or whatever, real, and for some images the label is synthetic. So it's just a binary classification. So you can score what is the current performance of the current parameters. We can get the score, right? And we can just backprop to update the parameter so that it's maybe the cross entropy loss should be lower or whatever it is. Okay, binary accuracy should be better. Now for this synthetic data, right, that we generated here, we pass it through. We have already passed it through the discriminator. And we know what numbers it produced. Remember, for the synthetic data that was generated, let's say the discriminator produced all numbers close to 0. Okay, that means it was not good output, because remember, generator's objective is to make numbers close to 1, right? So using the synthetic data, we got numbers close to 0 or 1, whatever. That can be used to score the generator. Close to 1, good. Okay. Close to 0, look at the gap, and close to 0 means generator's loss in some sense is high, and so you need to update the parameters. Okay? You can gradient update the parameters of the generator as well. Okay? That's basically what's going on, and explicitly. Okay, so those 2 steps that I talked about are just these 2 steps, which I'm gonna. How much time is there? Yeah, we have time. So this is the full objective function. Let's ignore the first equation for now. Let's focus on the last equation, which is about the generator, then talk about the discriminator, and then talk about the full equation. Okay. So what's the last equation saying? It's saying on the so this is z. Remember, z is the source of randomness. Okay, the input to the generator. On average, starting from this expectation you can kind of ignore, but on average, from averaged over my source of randomness, I produce an image g of z. D scored that image, that d of g of z, right? That score, is it close to 1? Is it close to 0? Okay. If the score is close to 1, then it's a log of 1 minus some number which is like close to 1. So a log of a very small number. Okay. Yeah, log of a very small number. Now, if it's close to 0, which is bad performance, then it's a log of 1 minus 0, which is a number close to 0. So, is it correct? Gradient descent. Did I flip anything? Okay. Yeah, this is fine. Yeah. So here we don't care about the decoder parameters, they are fixed. We want to change theta g so that we minimize this objective. Okay. So we want to change theta z so that we can get as low values for this as possible. Okay. How do we get low values? When d on the generated images starts scoring things as close to 1 as possible. Okay. The closer it produces, it gets confused, d gets confused. The smaller this number is. Log of 1 minus some number 1 close to 1 is nice. It's a small number. Don't worry about the log. It's just if I'm close to 1, then it's smaller. If I'm not close to 1, if I'm kind of saying that it is actually fake, then 1 minus 0 is a large number. Okay. So so it's very, so we want to change the generator parameters so that this number is low. Okay. Now that's gradient descent on the generator. Now let's go back to the discriminator. Discriminator is just a binary classification setting. So on real images, it has a score close to 1. On synthetic images, it has close to 0. Okay. So on real images, don't worry about the log part. On real images, we want to maximize this. Okay. Because we want to produce close to 1, high numbers. So remember the parameter theta d is the parameter of the discriminator. On real data, we want to get close to 1. On synthetic data, which is this produced by G's, we want to get close to 0. Okay. If we get close to 0, then 1 minus 0, if 0, then this number is high. Okay. So discriminator is trying to maximize its objective, which is this objective, and the generator is trying to minimize this objective. Okay. And in fact, these two objectives, you can just write it in a single expression where you have both the minimization over G and the maximization over D. Okay. Why? That's because this term here is exactly the same as this term there. Okay. So there is no, data is only appearing in one term, discriminator. Discriminator is scored high. But for the data generated by the synthetically by the generator is trying to minimize this term, whereas the discriminator is trying to maximize the same term. So that's this term. Okay. So this minimax are you're minimizing one set of parameters and maximizing another set of parameters, and that's why this is called minimax objective. Okay. Of this long expression, but this long expression is just one term is data related, one term is synthetic data related. And data related term only makes sense for discriminator because that's only fed into the discriminator. And the synthetic objective or synthetic data related term is part of both discriminator and generator. Okay. So that's the I guess the very mathematically heavy detailed thing, but I hope the operation is clear, right? So basically, discriminator, like this said, this is synthetic data and this is real data. Obviously, discriminator should be able to discriminate these two, and you kind of backdrop and update these. And while doing the And while updating the generator, you kind of lock this parameters of this generator. You're not updating it anymore. You're just trying to say, okay, whatever the previous parameters were, let's change the, if the numbers are not close to 1, something less than 1, then let's update the parameters so that you get close to 1. Okay. Any questions about this? This is the very like indirect way to update the parameters of the network so that it actually starts producing better and better images. So if you didn't follow like the previous expressions, but these two figures should kind of give you a sense of what's going on. What is a two-player game? The two players are just the two networks, and one is trying to classify between real and fake. The other one is trying to confuse the first player to say the fake ones are the real ones. Okay. And what are we training? The parameters of these players, like the parameters of the discriminator and the generator. If they improve, then they're getting better and better, and there's going to be some end to this game where, you know, either the discriminator gets defeated or the generator gets defeated, right? Okay, so I think we already saw the deep con network, right? So we saw that for VAE, and this network, when you use it, when the folks use it, they call the particular GAN DC GAN. Okay, just as a and that's a link in our lecture goals, and that's also the beginner tutorial on PyTorch website. Okay? So there they actually just do this. They define the same PyTorch model. We have seen it several times. Same, at least a model definition template we have seen. So it's exactly the same. And so we are pretty much done. That's pretty much the treatment of GAN. So we just have to describe what are the two networks and how are they improving themselves during training. How are you doing backprop? And once you're done with the training, you ignore the discriminator. Given a generator, you create some random Z, passes the generator, you get an image. Okay, and that's why this is faster than some of these. So that's why there was that GigaGAN or whatever. There was a paper that I showed where they kind of show that you can generate realistic images from text inputs, text to image synthesis, because you're only doing these types of forward passes. This is much faster than some of these stable diffusion and DALI type of models, which have to do this type of forward passes multiple times. Okay? So they were showing the capability of GANs to be able to still do text to image with high enough quality. So here's just a, again, GANs also retain some kind of continuity. So on the latent space, if you change some I mean, you basically go from one point to another in the latent space, in the Z space, the input of the GAN, then you can see a variation in like going from one image to the other. There's some continuity. I don't want to point out explicitly which object got, which windows were removed or which door became, which door got changed, but this is something from a paper from 2015. They showed how to, how it works after you've trained. Like this is just mostly like diagnostics of what was learned. Okay. Yeah, and very similar to, again, when you did embeddings, there was some brief discussion about some arithmetic, right? The embedding for king and embedding for queen. If you subtract it, you get a direction which is similar to the direction between, let's say, a man and a woman or something like that. So here, same thing. So if you look at the embedding for this person and the embedding for this person without the glasses, and you add the embedding for a woman, then you can generate these types of new images. Okay. And GANs still have it, but GANs have this issue called mode collapse, which is that because of this very indirect training process, if your original data looks like this, so think of it as a top view of a bunch of Gaussians. Okay, top view of a bunch of Gaussians. Then when you're training GANs, this is just the generator. What type of distribution is it start generating? Okay? So you could have what is called a mode collapse, which is that although the top view, from the top view, you can see that this data is multimodal. So it's like whatever 4 times 4, 8 modes, 8 peaks, basically. Think of them as hills, right? As the GAN learns, the generator network, as we're training, it's jumping between the modes and may not be able to capture all the modes. Whereas if you fix it, you may be able to kind of get the mode. So there's this issue of mode collapse, and there is some extra fixes that are needed to train these GANs. So GAN training, at least initially, a few years ago, people were concerned about this type of an issue. Not just this, but there are many other issues. But this was one of the predominant issues at that time. It's called mode collapse. I mean, we're not showing any solution, and we're not talking about it, but it's just one issue with training these types of things. And that's pretty much it for GANs. I mean, there's some experiments of here we are showing as a function of training, you get more realistic and realistic images as you generate as you train more, and that's pretty much it for GANs. So now what I want to do for a couple of minutes is just compare VAEs and GANs in terms of pros and cons. Okay. VAEs are generative models, so they actually explicitly, there is a likelihood function, there is a joint distribution, you can compute all sorts of things, expectations and conditional probabilities and stuff like that. They achieve higher likelihoods on data, but the generated samples have some issues. Okay, by the way, this characterization, this slide here is more hand wavy, so it's pretty rough and qualitative in nature. Basically, sharpness, of some of these VAE models, the sharpness of the images is not that high. Okay, they give like very diffused images. And you can you can compare generated images with original images, which is not possible with GANs, because GANs don't have any input images at all. Okay, at least the generative network doesn't see any input image. There is a training set, but an image generated by a GAN, the generative network, there is no corresponding similar image on the discriminator side. Okay, it's just comparing discriminatives, the set of real images with generated images. There is no 1:1 correspondence with, oh, there was an image of a cat, I should generate an image of a cat. There is no such thing. Okay. GANs, they're using a discriminator basically. They try to solve a game, so that solving a game means learning those parameters of the generative network and the discriminator network. That game is actually interactable, in the sense that it's not, you don't know what whether the game actually has an equilibrium, by the way. Why? Because the generative network and the discriminator network are just highly nonlinear functions. I mean, it's unclear, by iteratively incrementing or changing the parameters, you get somewhere interesting, or where, do you even get somewhere and stop or not? It's not clear. It tends to have sharper images, and there's a few more other points, but in the past, I guess 3 to 5 years now, there's like 1,000+ variations of each of these VAEs and GANs. Okay, so, but anyway, in terms of pictures, this is VAE. So there's an encoder, there's a related phase where you're assuming a Gaussian distribution, and then there's some decoding process. And given an X, it's easy to find Z because you can just use an encoder, and you have a probability distribution over all the outputs. And GANs, there is no distribution. So basically, you start with a random source and generate an image. Okay, so you don't get a kind of control on anything, but at training, you're trying to generate images which look similar, or which can confuse the discriminator. They don't have to kind of have one-to-one correspondence with anything. Here, there's a correspondence, right? So here, there's no such relation between images. At least in terms of figures, you can see that the generator is like the decoder in terms of like a decon network, and the discriminator is just a classifier. So you can think of it as a CNN. This is also like a CNN here. Yeah. Okay, so let's pause there. Any questions? No questions. Okay, so anyway, to summarize, we looked at VAE and GAN today, and we also briefly again recapped autoencoders. So next time, obviously, we'll talk about the projects that you should put a lot of effort on, and then after that, we're going to look at decision making. So we're going to look at basically reinforcement learning. I know some team wants to work on reinforcement learning, but we're going to start looking at the basics of reinforcement learning. Okay. Yeah, that's it.